Alright guys, let's see how we can solve another question from the first chapter of the Mechanics of Materials, Johnston. And we solved the question in the previous video about the concept of the load and resistance factor design. So in this video, we're going to solve another one in that concept, a little bit more complicated than what we solved in the previous one. And we have this 40 kilogram platform that is attached to the end B of a 50 kilogram wooden beam AB. And this is supported by a pin at point A by a slender steel rod BC with a 20 kilonewton ultimate load. So we have the ultimate load in here. And then in the A part of the question, it says that using the load and resistance factor design method with a resistance factor of 0.9, we have the load factor 1.25 and 1.6 for the dead load and the live load. And we need to determine the largest load that can be safely placed on the platform. Basically the load that can be placed on this platform. And in the B part, the question is saying what is the corresponding conventional factor of safety for the rod BC. So before we start, I'm gonna draw the free body diagram for this bar AB, and if we look at it, we'll see that we have a pin at point A, which means we have two component AX and AY. So we have the weight of this bar, which we can show it with W, maybe 2. So we have the weight that is attached in here. We're going to show this with W1. And we have the force that is in this steel rod BC. We're going to show that with P. So if we call that P, we have the ultimate load. So the ultimate load, or PU, is going to be 12 kilonewtons. So we're going to use that later in order to find the factor of safety, which we know is the ultimate load over the P. Okay, let's get back to our free body diagram. So we are in equilibrium. We're going to use our equilibrium equations. And if we use the moment equation for the rod AB, we're going to get rid of all the unknowns that we have at A. So we're going to do the moment about point A, counterclockwise moment, positive. And by the way, I have another channel for engineering mechanics specifically where I'm covering all these equilibrium questions and how to find the moment in 2D. So feel free to check that one out. I'll put the link in the description below. So this will be equal to 0, and we're going to have the moment of the W2, which is going to be in this direction. So we have a clockwise moment. So negative W2 times the distance. And since we have a rectangular beam, the centroid or center of gravity would be exactly at the center. So the distance would be 0.4 divided by 2, which is going to be 1.2 on each side. So this will be multiplied by 1.2, and we're going to have the moment of the W1, again, same direction, clockwise moment, so negative W1, and the distance this time is the whole length from A to B, which was 2.4. And for the force P, we have to figure out, like, first of all, we need to resolve this force into two components, one parallel and one perpendicular, and we can see that the horizontal component is not going to make any moment because it's going to pass through point A, but we have the moment of the vertical component, which is going to be counterclockwise, so plus P. Another question is how we're going to find that vertical component, and we're going to have this right triangle in here, which we know this side is 1.8 and the base is 2.4. So if we want to find the y component, if we just call this one alpha, so we have 1.8 at one base, or one side is 1.8, the base is 2.4, which if you divide them by 0.6, this will be 3, this will be 4, and the hypotenuse will be 5. So we can basically use that ratio. So our y component, if we just call our x and y in here, would be p sine of alpha, and sine of alpha would be the opposite over the hypotenuse, or 3 over 5, and the distance would be, again, the distance from A to B, which was 2.4. And this will be equal to 0. And now we can find, if we just bring everything to the right side other than p, and we can cancel out actually 2.4 from each of these. So we're going to get a 0.5 in here. So our P will be 5 over 3 W1 plus W2 times 5 over 3 times 0.5, or 1/2, which our P here would be 5 over 3 W1 plus 0.5 would be 1/2, so 5 over 6 W2. And that would be our biggest takeaway from this part of the question, that we can find P based on the W1 and W2. So now we can find W1 and W2 pretty easy. You just need the mass them and multiply that by acceleration of gravity, which we know is 9.81. And we're going to have the same thing for W2. So let's see what was W1. So W1 was the platform, which we know is 40 kilograms. So 40 times 9.81. Since the mass is in kilogram, we're going to get the weight in newtons. So 40 times 9.81, 392.4. And for the W2, we have the weight of this wooden beam AB, which we know is 50 kilograms. So this will be 50 times 9.81. Let's see what we get. So 490.5. So if you want to find the dead weight, or PD, we simply have 5 over 3 times W1, which was 392.4, plus 5 over 6 times 490.5. So this is our dead weight, regardless of our live weight, which would be the weight that we're going to put on the platform. This will be the same thing, and let's calculate this. So this is going to give us 1062.92 newtons as our PD, and that was our dead load. If you want to find the live load, so the live load would be what we have on the platform, which is consist of the W1, which is basically the mass that we are trying to figure out, or the mass of the load that is on here, or the box that I'm going to highlight in yellow, this one. And on the W2 part, we don't have anything, so we can find the live load in here, which is basically, if we get back to our P, we have 5 over 3 times W1, which is mass times acceleration of gravity, plus 0, because there is no load on that part, on the wooden part. So now that we have these two, we're going to go to our load and resistance criterion. So we had a formula in here, which was, and in this formula, the only thing that is missing in here would be our PL. So what we're going to find from this design criterion is that we're going to find the PL. And once we find the PL based on that formula, we can find the mass that we are looking for, or the live load that can be placed on that platform. So just have to have PL on one side. So we're going to have gamma in the denominator. So y times pu minus, and we have all of this in the question. So these are all givens, and we should be able to find the PL in here. So if we get back to the question, we have the resistance factor 0.9 times the ultimate load, which was 12 kilonewton, so 12 times 1000 in order to have it in newton. So that's that. We have all these other factors. So the gamma d is 1.25, so we have it in here, and the other one is 1.6, so 1.25. We figure out the dead load in the previous step, so dead load is what we have in here, 1062.92, and we're going to divide that by 1.6, so we're going to find PL in here. Let's calculate that. So that's going to give us 5919.59 newtons. And we know that PL is equal to 5 over 3 times mass times acceleration of gravity. So we should be able to find the mass in here pretty easy. 3 times 5990.59 divided by 5g. Our g is 9.81, and this is going to give us the mass. So this times 3 divided by 5 divided by 9.81. So this is going to be our mass, 362.05 kilogram, and that would be the load that we can put on the platform, or the allowable load. So that was the A part of the question, and the B part, we had to find the corresponding conventional factor of safety, which is the formula that I wrote in here. So we already have PU, and we just need to find the P, and our P is basically the dead load plus the live load, which we found both in the previous step. The dead load was what we had in here, 1062.92 plus PL. We found it from our design criteria, which was 5919.59. So let's see what we get. So our P will be 6982.51 newtons, and we should be able to find the factor of safety. We had the ultimate force or ultimate load 12 kilonewton, or 12,000 newtons, and that would be our PU, and our P is what we found now. So we're just gonna have 12,000 divided by answer, and this is gonna give us 1.72 as our factor of safety and the answer for the B part of the question. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next video. Have a good one.